Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to be looking at electromagnetism. Okay, we looked at in the last video about how the electrons within an atom can cause a magnetic field around the atom. And if you line up all those, then you can get a permanent magnet. Well, today we're going to look at electrons moving not inside the atom. Okay, which we've been studying this unit quite a bit, electrons moving through a wire. So if we have an electron moving through a wire, it turns out that that also will create a magnetic field around it. This was discovered in 1919 by a bloke named Hans Christian Oersted. He was doing something with circuits, and as he turned them on and off, he happened to have a wire sitting over a compass. At least this is the story I've heard. And when he turned on the circuit, the compass rearranged its direction. And of course, a compass is a magnet that's allowed to float somehow. And so the fact that it rearranged indicated that turning on the circuit must have somehow created a magnetic field. And so it turns out, as we began to analyze this magnetic field, that the magnetic field that it produces is tangential to the wire, meaning it's going in circles around the wire. Okay, so here's a little diagram of this. You can see that as the current, which is these red and green dots, moving through a wire, create a magnetic field that we can see going around the wire here. So the question is, there are really only now two options left. Either it goes around the wire this way, or it goes around the wire this way. So those are kind of the two options that we have. So in order to remember which way it goes, we use our right hands. Okay, go and raise your right hand. No, the other one. So your right hand, good, we're going to see how that works. So in order to use the first right hand rule, you stick your thumb the direction of the conventional current. Now keep in mind, conventional current goes the direction a positive charge would flow. So if you're looking at a battery, that would be from the negative side, or from the positive side, away from the positive side, because positives would repel from positives, and toward the negative side of a battery. Okay? Of course, that's the opposite of the direction the electrons are actually flowing. But convention, thanks to Benjamin Franklin, 150 years before the electrons were discovered, determined that the direction a positive charge would flow is the direction of our conventional current, and so that's the direction our thumb will point. So we point our thumb with the conventional current, and we can see that our fingers only wrap, naturally bending, without breaking them. They bend one way around your thumb. Okay, so in this case you can see here as the current is going this direction, the magnetic field wraps around it in this direction. Now, if we were to flip the current, okay, and have the current go this way, okay, then our thumb would now go that way, and now the magnetic field would wrap the other direction around the wire, as you can see in the animation here. So now that we're dealing with things in 3 dimensions, it gets a little bit harder to draw them, okay, because we have, a current going this way, and above that, the magnetic field is going into the computer screen. Behind it, it's going down. Then underneath it, it's coming out of the computer screen, and then it's going up. Okay, so we get these directions as well as this direction. So since they're really kind of 6 basic directions, we need 6 ways to draw arrows. Well, some of those are easy. We can draw an arrow pointing to the right. We can draw an arrow pointing to the left. We can draw an arrow pointing towards the top of the screen or the top of your paper. And we can draw an arrow pointing towards the bottom of your paper. Now, the trickier thing is to draw an arrow pointing into the screen or an arrow pointing out of the screen. Okay, so if we think of it in terms of an arrow, like a bow and arrow, if you were to see an arrow coming at you, you would see the point of that arrow. So we draw an arrow coming out of the page like this, a circle with a dot in it. And we draw an arrow going away from us. If you were the one shooting the bow and arrow, you would be looking at the tail feathers. You know, arrows really do have 3 tail feathers typically, but since we're not big fans of Mercedes-Benz, we draw our tail feathers on our arrows like this, an X inside of the circle. And that means in that wire, or the magnetic field at that point, is going away from the computer screen, okay, or away from your paper if you're drawing it on paper. Now we can draw arrows in 6 ways, but how are we going to recognize what's going on in a picture? Well, there are 2 kind of main ways, 3 ways you could draw a diagram of something on a paper, of a location. Okay? One is you could just pretend like it's hovering in front of you, in which case you have the right and the left and up and down and away from you and towards you. Okay? On the other hand, you might be looking at something from like a map view, in which case now the top of the paper is no longer up. The top of the paper is north, and the bottom of the paper is south. The right side of the paper is east, and the left side of the paper is west. And coming out of the paper is now going up, away from the earth. And going into the paper is now going into the ground, or down. Finally, you could also take everything into Cartesian coordinates, positive y, positive x, positive z, negative z. Okay? So those are 3 ways we can define it. Usually we'll use one of the first 2, either a map view or a what's sitting in front of you view. I'm not sure what to call it, portrait view, maybe. And so those are the ways that we'll draw our pictures. So now let's say you might get a problem with something like this. Let's say there's a wire and the current is traveling from east to west through that wire. What direction will the magnetic field be above that wire? Okay, you can see it, the wire drawn in cardinal directions, north, south, east, west, up, down. Okay, and so if we have a current going from east to west, so my thumb will go this direction, east to west, okay, and then I can see my fingers are wrapping around it like this. Okay, so if the screen here is a map of the United States, then or wherever, but we have east, we have west that direction, east this direction. This direction is north, this direction is south. Okay, so above it would be out here, and above it out here we can see my fingers are pointing up. Remember, it has to be going in a circle around this. So if it's going to be on this side of the wire, it has to be either up or down, and the right hand rule tells us up. Okay? If we were to come up here to the north of the wire, then it would be going into the ground. If we were going to go under the wire, it would be going south. And if we were going to come south of the wire, it's a little bit harder to do here. Okay, south of the wire, then it would be coming up. Okay, out of the screen. If we want to do the same problem using a first-person perspective, if it's going from, what is that for you? From right to left, then you put your thumb right to left, you wrap your fingers around it, you could say above it, it's going what direction, and so you would say going away from you. For me, it's towards you, but I'm doing it from your perspective, so it would be going away from you. That is the first right-hand rule, and how you would use it to understand the magnetic field produced by a wire carrying a current. Now keep in mind that if you change the shape of your wire, so you bend your wire into a loop, and so the current is now going in a loop, okay, well, just pick one point on that loop, do the right-hand rule, and you know what magnetic field that part of the loop is is producing. Move your thumb to a new part of the loop, okay, and do the magnetic field around it. Move it to a new point and do it around it. And you'll see that, as you can see as I'm doing this, if the current's going this way around the loop, okay, the magnetic field in the center is all pointing one direction. Well, that's how we produce an electromagnet. You wrap a wire a whole bunch of times, and the magnetic field to the center of that is all pointing one direction, so you get a big magnet. You can put a iron nail or iron bar in the center of that to help, which will cause all of the little magnets in that iron bar to align as well, increasing your magnetic field strength. And you can use it to do things like pick up cars. Pretty cool. So electromagnetism. Oh, but the best thing about using an electromagnet to pick up the car is that when you want to drop the car, you can just turn off the electromagnet and it falls. It's a beautiful thing. All right. Hope you enjoyed learning with us on electromagnetism. We'll see you next time.